Hi again, this is Dr. Rebecca Garris, Colorado School of Mines. I'm making this video for my students explaining the activity from yesterday, which was Tuesday, April 13th, 2021. So this is from chapter 11, section 1, day 2. And this one, I definitely wanted to get some feedback, but I'm just not thinking I'm going to have enough time with grading exams. So instead, I'm working through the activity and just talking my way through it as if I was working on it for the first time, which I'm totally not. Okay, I kind of am. But that means, bear with me if I have some mistakes. I'll try to fix them as I go, though. Okay, so we're looking at the Taylor polynomial error bound, which has some pretty formal jargon here. If you look at number 1 under the learning outcomes. So we're gonna talk through it, and I'll explain to you how I make the choices that I make, and hopefully that will help you make the choices as well. Now this builds on the activity from 11.1 day 1, and I've made a video on that too. So if you have any concerns about how to come up with the Taylor polynomials, how to do those computations, please watch that other video. I think it would be really helpful. Okay, let's jump in. Activity number 1. Suppose you would like to use a degree 2 Taylor polynomial for f of x equals e to the x to estimate e to the minus 0.15. Why is a equals 0 a good choice for the center? So that's a good question. We can just start with that. So we have f of x equals e to the x. F of x equals e to the x. That means that e to the minus 0.15, oh, I didn't write that right. The minus 0.15 is equal to f of minus 0.15. So why is a equals 0 a good choice for the center? Basically because minus 0.15 is close to a. Is close to 0. Right? That's basically what that first question is answering. So I'll highlight that as my first answer. Recall that P2 of x is equal to 1 plus x squared over 2. And that's a degree 2 Taylor polynomial for f of x equals e to the x, centered at a equals 0. That's something that you did in your pre-class work on the first day of section 11.1. Use this to make your approximation for e to the minus 0.15 and use the error bound formula to determine a bound on the error in your approximation. Okay. So I have my P2 of x. So that means that f of minus 0.15 is approximately equal to P2 of minus 0.15. And that's equal to 1 plus minus 0.15 plus minus 0.15 squared over 2. And we can put that into our calculator. So let me see. 1 minus 0.15 plus 0.15 squared divided by 2. And I get that this is equal to 0.86125. Usually I only keep 3 decimal places, but since, there's only 5 of them, I'll just keep it. And in this one, the error bounds might be fairly small, so I'm going to try to keep more decimal places than I did in my previous video. Okay, so that's my estimate for e to the minus 0.15. Okay, so now I want to use the error bound formula to determine a bound on the error in my approximation. Okay, so let's look at this error bound formula. The actual error would be f of minus 0.15 minus P2 of minus 0.15, which is less than or equal to m divided by, notice here I have n equals 2, which means n plus 1 is equal to 3. So I get a 3 factorial times x minus 0 cubed. Oh, and it's not even x. Let me see. Let me do that again. Minus 0.15 minus 0 cubed. Okay, so this is now what I'm trying to find. 3 factorial is a number, minus 0.15 cubed is a number, and now I just need to figure out what m is. So choose m. What I know is that m is the maximum of f triple prime, the next derivative, the third derivative of x on the interval from minus 0.15 to 0. Okay, so what is f triple prime of x? Well, our function is e to the x, and every derivative is just e to the x, so f triple prime of x is equal to e to the x. And really, I should have put absolute values around that. It's the maximum of the absolute value of f triple prime of x. Not a big deal here because we don't have a minus sign, but if there was a minus sign, you would want to just ignore that. Okay, so what do we know about e to the x? E to the x is always increasing. So that means that e to the 0 will be the largest value on this bound, on this interval. So I'm going to choose m equals e to the 0, which is the upper bound of this interval, and e to the 0 is equal to 1. Okay, so that means my error, this is like R2, R2 of minus 0.15 is less than or equal to 1 over 3 factorial, which is 6, times 0.15 cubed. Because 0.15 is the absolute value of minus 0.15 minus 3. And what is this equal to? 0.15 to the third power divided by 6 is equal to 5.625 times 10 to the minus 4. So that means my error equals, this is the upper bound on the error. And that would be my answer. Okay. So what is the actual value? Actual error. If I plug in, let's see, this would be equal to e to the minus 0.15 minus 0.86125, which was my approximation, and I'll just put that in absolute values. Let's see. E to the minus 0.15 minus 0.86125, and that's negative, but I'm getting, let's see, 5.4 times, or 5.42 times 10 to the minus 4. So, in fact, the actual error is less than the error bound, which is guaranteed by the theorem. Okay, so the important part here is choosing M. Make sure you justify. This is where I justified it. F triple prime is always increasing, so I choose M at the upper bound of my interval. In this case, that made M equals 1. Okay, let's do the second one. Use a degree 4 Taylor polynomial to estimate ln of 1.1. Determine a bound on the error in your approximation. Recall, we have our 4th degree Taylor polynomial, which I made in my previous video, so you can go watch that if you want. So we have the 4th degree Taylor polynomial for ln of 1 plus x centered at a equals 0. Why is this a good choice for f of x and center a? Okay, so we want to determine ln of 1.1. which is equal to ln of 1 plus 0.1, which in this case would be, if this is our f of x, if f of x is ln of 1 plus x, then this is equal to f of 0.1. And 0.1 is close to 0. So there you go. That's my explanation for why this is a good choice. So now we'll estimate ln of 1.1. ln of 1.1 is approximately P4 of 0.1, because again, this is what we're looking at, ln of 1 plus x, so x in this case is just 0.1. That's equal to 0.1 minus 1/2 times 0.1 squared plus 1/3 times 0.1 cubed minus 1/4 times 0.1 to the 4th. And we can plug that into our calculator. 0.1 minus 1/2 times 0.1 squared plus 1/3 times 0.1 cubed minus 1/4 times 0.1 to the 4. And I get that this is equal to 0.953083. I don't know, I could keep going, but that's the edge of my page. So I'm going to go with that. Okay, and determine a bound on the error in your approximation. So here we have a 4th degree Taylor polynomial. So that means n equals 4. So that means we're finding the remainder. The 4th remainder evaluated at 0.1 is equal to f of 0.1, which is ln of 1.1, minus P4 of 0.1. And we are guaranteed that's less than or equal to m over n plus 1 factorial, which is 5 factorial, times the difference, 0.1 minus 0 to the 5th. Again, those two are just numbers, so we need to figure out what n is. Oh, and here we're going to want to go back. Let's see. So what we found, I'm going to look at my notes. This was number 3 on the activity from yesterday. So what we found was that the 4th derivative of x was equal to minus 6 times x plus 1 to the minus 4. So that means that our 5th derivative of x is equal to 24 times x plus 1 to the minus 5. So we are looking at the maximum value of this in order to choose m. Okay, so the 5th derivative, this thing, x plus 1 to the minus 5, means that on the interval, right, from 0 to 0.1, what's happening? So as x gets bigger, f to this 5th derivative of x gets smaller. So this is always decreasing. So that means we choose m is equal to the 5th derivative of x evaluated at the lower end. It's decreasing that, so that means it's going to be a larger value at 0 than at 0.1. And if we plug in 0 into x plus 1, we just get 1. So 24 times 1 to the minus 5 is just equal to 24. So that's our m value. So there's our justification, and we're going to do that. Okay, So that means that R4 of 0.1 is less than or equal to 24 over 5 factorial times 0.1 to the 5th. I plug that in. I get 24 times 0.1 to the 5th. And then divided by the quantity, 5 times 4 times 3 times 2 times 1. I'm sure there's a factorial button in my calculator, but I don't see it. So I'm just going to write it all out. Okay, so I get that this is equal to 2 times 10 to the minus 6. Oh, that makes sense. 24 is actually equal to 4 times 3 times 2, which is 4 factorial. So I'm just left with 0.1 to the 5th divided by 5. All right, so there is my error bound. Okay, and let's see. This was my value up here, and we could check our work if we want. If I put ln of 1.1 into my calculator, I get, 0.0. What am I missing? I'm off by a factor. Oh, you know what? I wrote down this one up here wrong. There's a 0 in front. It's 0.0953083. There we go. That makes more sense. Okay, so ln of 1.1 in my calculator is 0.0953101. So you can see it's actually very close. It's off by, that later power. So let's see. If I subtract our result that we got, 0.0953083 from ln of 1.1 on my calculator, I get the actual error is equal to 1.88 basically times 10 to the minus 6, which is indeed less than 2 times 10 to the minus 6, as guaranteed by the Taylor polynomial remainder theorem. Okay, so there's 2 examples of how to use this. We can keep going, but I imagine some of you are probably done. So if 2 examples is enough, you can just stop there. But I'll keep going. Or if you want to see how to use the graph, you can fast forward if you want. Okay, so we're going to now use a degree 2 Taylor polynomial to estimate square root of 4.2, determine a bound on the error in your approximation. Recall that we got this Taylor polynomial second degree yesterday when we worked on that in the activity, when we did that for square root of x centered at a equals 4. So this again, this is going to be our f of x here. Why is this a good choice for f of x and center a? Let's see. So square root of 4.2 would be equal to f of 4.2, and 4.2 is close to 4. So that's my justification, and that's good enough. Okay, so first we want to use our polynomial to estimate 0.42, or square root of 4.2. Square root of 4.2 is approximately equal to P2 of 4.2, which is 2 plus 1/4 times 4.2 minus 4, which is just 0.2, minus 1/64 times 0.2 squared. And we can plug that into our calculator. 2 plus 1/4 times 0.2 minus 1/64 times 0.2 squared. And I get 2.049375. Cool. Okay, so that's my approximation. Now we figure out what is the error bound. We have a second degree, so n equals 2, which means we're looking at the second remainder evaluated at 4.2, which is equal to the difference between square root of 4.2 minus p2 of 4.2. And we are guaranteed by the theorem that that is less than or equal to m over 3 factorial times the quantity 4.2 minus 4 cubed. And now we just have to figure out what m is. Okay, so what did we have as our second, let's see, our f double prime of x based on our work yesterday. I'm going to go back to that. That was number 2 on our work from yesterday. The second derivative was minus 1/4 x to the minus 3/2. So we need our next derivative. F triple prime of x is equal to 3 over 8 times x to the minus 5/2. Now again, we have x growing in the denominator, which means this thing is decreasing everywhere. And specifically, decreasing on the interval, which we care about, which is 4 to 4.2. So if it's decreasing on the interval, that means we want to plug in the lower bound. So we choose m equals f triple prime of 4, which is equal to 3 over 8 times 4 to the minus 5/2. Do I actually want to calculate that? Not really. So I'm just going to leave it as that. Okay. So then our 2 of 4.2 is less than or equal to 3 over 8 times 4 to the minus 5/2 times 1 over 6 for the 1 over 3 factorial, and then times 0.2 cubed. And I'll just plug that into my calculator. 3 divided by 8 times 4 to the parentheses minus 5 over 2 times 1 over 6 and times 0.2 cubed. And I get that that's 1.5625 times 10 to the minus 3. Did I get that right? Let me just check my work. 3 over 8 times 4 to the minus 5 over 2 times 1 over 6 times 0.2 to the cubed power. Okay. All right, I think that's right. So that is my remainder. In my notes, I have a minus 5 power, so I'm just wondering if my notes are wrong or if my work right now is wrong. But we'll see. We'll see where the error actually is. Okay. So what is the actual error, right? What is the square root of 4.2? Square root of 4.2, let's see, the square root of 4.2 minus our guess here, or our approximation, 2.049375. I'm going to plug that in. And that's equal to 1.515, etc., times 10 to the minus 5. Which is, yeah, much smaller. I feel like I calculated this other thing wrong, though, so. Oh, well. Okay. Anyway, there we go. There's the actual error. So if somebody wants to figure out if I made an error, let me know. Oh, wait. No, I just copied it down wrong. Okay. There you go. This power should be a 5. And still, our remainder, our guaranteed upper bound of a remainder is larger than the value, the actual error. All right, one more. Let's look at number 4. Use a degree 5 Taylor polynomial centered at a equals 0 for f of x equals inverse tangent of x to determine, to estimate pi. Note that p5 of x is equal to x minus x cubed over 3 plus x to the 5th over 5. And then determine a bound on the error in our approximation. Okay, so where do we get pi? We want to estimate pi. How do we estimate pi from inverse tangent of x? So, and let's see, centered, we want something that's near a equals 0. So we can get where tangent of x, inverse tangent of x is equal to pi over 4. So what is that? Inverse tangent of, let's see, is that root 2 over 2? Let me think. Inverse tangent of 1. That's what I'm saying. It's when sine and cosine are both root 2 over 2. So inverse tangent of 1 is equal to pi over 4. So if we just multiply that whole thing times 4, we should get pi. So 4 times inverse tangent of 1 equals pi. That's what we're going to be looking at. That's what we're going to use to start with. So this one required a little bit of cleverness even before to figure out what x value we're using to estimate pi. Now, is 1 close to 0? Hopefully. So hopefully this would be a good estimate. I can't think of anything that would be a better fit, that would be easy. So we'll just go with that. Okay, so this means we're looking at inverse tangent of 1. So let's figure out what let's see. This should be approximately equal to 4 times p5 of 1, right? Because this is our approximation for inverse tangent of 1. There we go. So we're going to find our approximation and then plug it in. Okay, so 4 times p5 of 1 is equal to 4 times 1 minus 1/3 plus 1/5. So that's going to be our approximation. We'll see how close that is to pi. 4 times parentheses 1 minus 1 over 3 plus 1 over 5. That is equal to 3.46667. Really, the 6's keep repeating. So I've, approximated that a little bit. So that is my estimation. That's pretty cool. That's pretty close. I mean, I know it's 3.14159, but, we've at least got the 3 correct. Okay, so let's determine a bound on the error in the approximation. Okay, so the error, again, what we're finding the error on is p5 of 1. So presumably this has 4 times the error of what would be p5 of 1. So what does that mean? Okay, so the error, let's first find the error in, let's see, pi over 4 minus p2 of 1. Or p5 of 1, sorry. Because actually, right, p5 is approximately pi over 4. Okay, so we'll find this error first, and then, we'll have to multiply it by 4 to get the error in our pi approximation. Okay, so the error in pi over 4 calculation is, okay, it's going to be, we'll just call it R5 of 1, which is less than or equal to m over 6 factorial times the absolute value, 1 minus 0 to the 6. And how do we get m? We're told that this graph here is the 6th derivative of f of x. And what is the maximum value between 0 and 1? It's going to be right here. So whatever that is. And it looks like maybe the value is 101. So, because it's the line is like just slightly above the 100. So I'm going to say from graph, choose m equals 101. And you could choose 100 too. It's pretty close. But I don't know if that would be enough. So it's, I don't know. You could even choose like 105 or something. Let's try 101. 101 divided by 6 factorial times 1 to the 6, which is just 1. Let's see how close we are. 101 divided by the quantity, 6 times 5 times 4 times 3 times 2 times 1 is equal to 0.1402778. And really the 7s just keep repeating. Okay. So that was important for my justification. This is my bound on the error. And then, or that's a quarter of my bound on the error. So maybe I will actually take that away. Error in pi is equal to 4 times the error in pi over 4. So that would be less than or equal to 4 times this number we just had, which would be 0.561111 forever. It looks like it's repeating. Okay. And what is the error that we got? Pi minus 3.466666, whatever. And then the absolute value of that. Actually, the error is pi minus 4 times our approximation, or times the polynomial approximation, which is exactly equal to, we'll do it, absolute value, 0.325074, etc., which is definitely less than our error bound. So that checks out. Okay. Cool. So that one was a little bit harder. We used a graph. We had to figure out what our x value was. And then we had to do 4 times our error. So that was an interesting complication. All right. So if you have any questions about this, get back to me in email or in office hours, or we can talk in class. Anything you want. I'm here to help you. All right. Thanks.